In this video, I'm going to show you some basic vocabulary related to multiplication. And what we're going to start with is learning about something called a rectangular, let me move this down, rectangular array. So what I have here is a whole bunch of counters. I have 12 counters here, in fact. And it doesn't really matter how many counters I have. I could always arrange that, however many number of counters I have, into a rectangle shape. So what I'm going to do is I'm going to show you an example of that. I'm going to put these into a rectangular array. And you can see I've now made a rectangle. I have in every one of these vertical arrangements, which we call columns, I have the same amount of counters, 3. And every one of these horizontal arrangements right here, which we call rows, I have the same amount of counters, 4. So this is a rectangular array. It wouldn't be a rectangular array if I removed one right here, because my rows would not all have the same number of counters in them. But in this case, I can give this rectangular array a mathematical name, and that mathematical name is going to be called a number model for that array. And that number model for this array is 3 times 4 equals 12. Because there are 12 counters here, and I have 3 groups of 4. These two parts right here, the 3 and the 4, are called factors. And the 12 right here is called the product. The product is a solution to any multiplication problem. So if we were just to say a generic number model, and any number model must always have some numbers in it. It must always have an operation, whether it's add, subtract, multiply, divide, and it must have a solution. So we do have an example of a number model here. We have some numbers that in this case are called factors. We have an operation that's multiplication, and we have a solution that is the product. The 3 and the 4 in this case, 3 and 4, are called factor pairs of the number 12. Now, what I'm going to do next is I'm going to show you some other factor pairs, some other ways that we can make in a rectangular array from these same 12 counters. So let me clear this off and get another sheet of paper here. And I'll put my counters back on here, and this time we're going to try to arrange them in a different rectangle. So instead of a 3 by 4 rectangle, this time I'm going to arrange them. Oh, let's do it like this, in a 2 by 6 rectangle. Now this is a rectangular array because every column has 2 in it and every row has 6 in it. We would say that this is the number model is 2 times 6 equals 12, and 2 and 6 are a factor pair of the number 12, just like 3 and 4 are a factor pair, 2 and 6 are. I can also actually turn this like this, and this now becomes a different number model. Even though I didn't actually change the array at all, it's still exactly the same number of counters arranged in exactly the same configuration. Because I turned it, now I have these become my rows. I have rows of 2 instead of rows of 6, and these become my columns. I have columns of 6 instead of columns of 2. So this problem now becomes 6 times 2 equals 12. Now notice that the factor, let me move that down so you can see it. Notice that the factor pair is still the same. 6 and 2, 2 and 6 is still the same numbers, but their order has changed. And that's something that's special about multiplication, is that we can change the order. We can change 6 times 2 or 2 times 6 and still get the same product. In the past, you've called those turnaround facts. But there's actually a fancy name for that, and it's called the commutative property of multiplication. That's an E right there, of multiplication. And the commutative property of multiplication says that the order in which you list the factors does not matter. 2 times 6 is the same thing as 6 times 2. A times B is the same thing as B times A. So let's see if we can make any other arrays out of these 12 counters. I'm going to slip another sheet of paper in underneath here. I can think of one other way that I can do this, and that is just to make one big long column of counters. And I'm going to have to kind of squeeze these in. It may not fit all in the counter underneath the camera at once, but I'll move it back and forth so you can see that I have one big long column of 12 counters. So I can say this is a 1 by 12 array, or if I turn it this direction, I can say it's a 12 by 1 array, and I can say 12 and 1 are factor pairs of 12. So if I wanted to list all of the factor pairs of 12, the number 12, I have 1 and 12, I have 2 and 6, and I have 3 and 4, and I could turn those into multiplication problems by writing it like this: 1 times 12, 2 times 6, and 3 times 4. And then I would also have the turnaround facts for each one of those, because multiplication is commutative. So I would also have 12 times 1, 6 times 2, and 4 times 3. So that's how we can make rectangular arrays from any number of counters. But believe it or not, I can have any amount of counters. I could have 1,253 counters, and I could still make a rectangular array. And the reason for that is that 1 is always a factor of any number. And therefore, I can always make a 1 by something array. Matter of fact, that number, I don't even remember what it was, but 1,253, or any other number, I can make a 1 by 1,253 array. Now that would be a rather long stretch of counters, and it wouldn't be a very efficient way to represent that number, but it would be a rectangular array. Let's look at one other example, and in this case I'm going to add a few more counters. This time we're going to use 16 counters. And we're going to try to arrange our 16 counters. Let me put 4 more on here. We're going to arrange 16 counters into a rectangular array. And the first thing that comes to mind is 16 is even, so I'm going to use 2 rows, because I know I can split any even number into groups of 2. So there we go. I definitely have a rectangular array. All of my columns have the same number, and all of my rows have the same number. So I can say that this is the number model for this is 2 times 8 is 16. Or if I turn it this direction, it's the same value, but the number model changes to 8 times 2 is 16. And we can say that 2 and 8 are factors of 16. Well, I obviously can also do this as one big long stretch. I'm not even going to arrange it this way, but I can definitely do it as one big long string of counters, and that would be a 1 by 16 array. If I did this, it would go off my sheet of paper, so I'm just going to write this down. Or a 16 by 1, same value. So I could also say 1 and 16 are factors of 16. But there's one other way that I can arrange this, and that is going to be with 4 rows and 4 columns, because 4 times 4 equals 16. So you'll notice in this one, 4 times 4 equals 16. What do you think the turnaround fact for this is? You'll notice that this is a special type of rectangle, And in this special type of rectangle is actually called a square. A square is a special type of rectangle. It just happens to have all sides equal in length. So the turnaround fact for 4 times 4 equals 16 is the same thing. 4 times 4 equals 16. This is actually a special, that's because 16 is actually a special kind of number. 16 is what's known as a square number. And a square number is any number that can be represented by a square array. And the reason it can be represented by a square array is because 4 squared, and that's what this means, it's called an exponent. 4 squared means 4 times 4, and 4 times 4 equals 16. And if I were to draw around this, you would see that it actually is a square shape. So if we think about it, we probably can think of some other square numbers. And I'm not going to model all these, but if we think about some other square numbers, if I made a 1 by 1 array, 1 would be a square number. If I made a 2 by 2 array, that tells me that 4 is a square number. A 3 by 3 array tells me that 9 is a square number. Of course, we already knew a 4 by 4 array told me that 16 was a square number. A 5 by 5 array tells me that 25 is a square number. So I'll let you keep thinking about that and see if you can think of any more numbers that are square numbers that will have square arrays. But I want to end this video by posing one more question for you, and this question will be answered in another video to follow. But do all numbers have an even number of factor pairs? And for you to think about that, let's go back to this 16 here. These are its factors: 2 and 8, 1 and 16, and 4 and 4. If we go back to 12, we have 1 and 12, 2 and 6, and 3 and 4. Do all numbers have an even number of factors, or do some numbers have an odd number of factors, and why? So think about that, and to get the answer, watch my another video on square numbers, and I'll dive into that a little bit more deeply.